Hi everyone, my name is Hamid Jaaru from UC Irvine, and this is a short presentation on Jaaru, which is an efficient model checker for persistent memory programs. This is a joint work with Harijo from UCLA and Brian Dembski from UC Irvine. Developing programs for persistent memory is challenging since these programs need to guarantee crash consistency. The challenge is raised because there is a volatile cache between CPU and persistent memory that delays the persistency of store instructions. Therefore, a system crash can cause either data not become persistent at all or the persistency order to be different from the program order. Modern CPUs provide special cache instructions such as CLFlush in x86 to enforce cache lines to be written back to persistent memory in a correct persistency order. It's very challenging to properly use these instructions to make programs crash consistent. So, testing persistent memory programs to ensure they are correct with respect to failures is very difficult. This is because exposing a bug requires the machine to fail at a specific instruction and depends on the state of the cache before the crash. So, there is a need for a model checker that can explore all crash behaviors of the programs to find bugs in them. We investigated persistent memory programs and we made an observation that makes model checking practically feasible for them. In fact, we observed that these programs need a way to verify the progress of pre crash execution and determine which data has been written out to persistent memory. One common technique is to use commit stores. These commit stores indicate that prior stores have been successfully flushed to persistent memory, and in post crash, the program just reads from these stores to determine the data is consistent. For example, there's a persistent tree data structure, and we want to add a subtree to its root. First, the program creates new nodes and properly updates their values and references. Then, the newly created subtree is being flushed to persistent memory. Finally, the program updates the pointer from the root of the tree to the subtree. This pointer is a commit store. In post-cache execution, if this pointer isn't null, it shows the insertion operation was successful. But if the pointer is null, there are a lot of possible memory states in post-cache, but all these memory states correspond to one unique post-cache execution, and that is the insertion operation failed and the program needs to recreate and reinsert the subtree. Our insight is to leverage commit store pattern and enumerate executions instead of memory states to make model checking practically feasible. Based on this insight, we implemented Jaaru to exhaustively explore all possible executions to find crash consistency bugs in the programs. Jaaru does not require any annotations or modifications on the existing source code. Also, it does not generate any false positives or false negatives. Any bug it reports is a real bug with the corresponding execution trace leading to the bug. Jaaru is capable of simulating complicated crash scenarios with more than one crash for testing the recovery code. It uses a constraint-based refinement technique to reduce the search space. The idea is to reason about the last time each cache line was flushed to persistent memory. To be more specific, Jaaru uses flush instructions to infer constraints on the last time each cache line became persistent in a pre-crash execution and refines these constraints in the post-crash execution to narrow down when a cache line is actually written back to the memory. To illustrate the idea, let's look at an example. The program executes instructions in the pre-crash code prior to the failure. Then it executes the instructions in the post-crash code. Both variables x and y are located in the same cache line. The blue line shows the order that stores were written to the cache. After the program executes the store y equal 1 and x equal 2, it performs a CLFlush instruction. This instruction flushes the cache line that holds x and y to persistent memory. At this point, Jaaru infers the constraint that this cache line must be flushed during the interval from CLFlush to positive infinity as represented by the red line. After the CLFlush, the program performs the store y equal 3, x equal 4, y equal 5, and x equal 6, and finally, the power is lost and the program fails. The red interval indicates that when the machine is powered back up, the persistent storage may have the values of 2, 4, and 6 for variable x, and 1, 3, and 5 for variable y that the post-crash execution potentially can read from them. Suppose the post-crash execution reads the value 4 for variable x. This tells us that the cache line must have been flushed sometime after the store x equals 4 and before the store x equals 6. So Jaaru refines the constraint to be from x equals 4 up to x equals 6, which imposes a much tighter bound on the cache lines interval. Now, if post-crash executions reads from variable y, the program only can read the values 3 and 5, and it doesn't see the store y equal 1 anymore. Our constraint refinement approach works well for persistent memory programs because it effectively leverages commit store pattern. In fact, Jaaru does not eagerly enumerate all pre-crash stores. Instead, it lazily enumerates a small subset of them that are actually read by the post-crash execution. So in our previous example, if there was a variable z with multiple stores in pre-crash execution, but the program never reads from them in the post-crash execution, Jaaru does not enumerate executions for different values of z since it does not expose a new behavior in the post-crash execution. This technique yields extra efficiency for Jaaru in pruning the search space to avoid exploring redundant executions. Although the complexity of Jaaru, like other model checkers, is exponential in general case, for programs that follow the commit store pattern, it has quadratic complexity in the length of the execution. If a program does not use commit store pattern, Jaaru can still significantly reduce the search space compared to naive model checkers in cases in which post-crash execution do not read from some of the unflushed stores. To use Jaaru, the persistent memory program has to be compiled with Jaaru's LLVM frontend, which instruments memory and cache instructions. Then, after running the program, the scheduler identifies potential crash points and the runtime system runs the program and simulates crashes. Jaaru analyzes the executions and refines the corresponding constraint for each cache line. If it finds bugs in the programs, it reports them to the user. Otherwise, it repeats the process until there are no more executions. We have evaluated Jaaru with FastFair, CCCH, recipe, and PMDK benchmarks, and we found 25 persistency bugs that 18 of them haven't been reported before. The majority of these bugs cause the program to crash due to assertion failures or illegal memory accesses. Some of these bugs are atomicity violations in which a partially completing update leaves the data structure in an inconsistent state. Jaaru can identify different types of bugs, including missing fences, missing flushes, and misordered stores and flushes that can cause atomicity violations. At the end, Jaaru can model check each recipe program in less than 15 seconds. Compared to previous model checkers, Jaaru reduces the search space orders of magnitude and it is much faster. For instance, for PART program in recipe benchmark, Jaaru only explores 174 executions compared to YAT, which needs 10 in power of 34 executions to fully model check the program. Please refer to our full presentation for more details about Jaaru. Thank you.